Hey guys, Mr. B here. So this video I'm going to be going over the chapter 26.1 notes. If you are struggling with maybe learning information and you just want to hear me talk about things and go over it like you would in class, that's what this video is for. So in this section we're going to be learning about the sun, how the sun works, different layers of the sun, how it's structured, some features on it, things like that. So let's begin talking about how does the sun produce energy. So if you ever look at the sun, you might think it's like a giant ball of fire, right? Like just flaming up in the sky. But obviously it can't be on fire because most of you probably know that in order for fire to work, it needs oxygen, right? If you ever had a candle and you've put a cup over it before, eventually the candle will go out because all the oxygen gets used up. Well, in space, there's no oxygen, right? If you go up into outer space and you don't have like a spacesuit on or anything, you can't breathe, you'd suffocate. So how is it possible then that the sun is burning if there's no oxygen in space? Let's first talk about how the sun gives off energy, and then we'll answer that question of, well, how does it produce energy? So when the sun gives off energy, it gives it off in the form of electromagnetic radiation. This is a very just fancy way of saying light, okay? Light is radiation, the same kind of radiation that can make you sick or that can give you cancer or that's harmful for you. That's what light is. Now, when I say light, you probably think of like, light. Oh, there's light. I can see things, right? Like a light bulb on. That's just one kind of light, okay? That's visible light, which is the light that your eyes can see. But light comes in many different forms. So microwaves is a form of light. X-rays are a form of light. Radio waves are a form of light. Gamma rays are a form of light. Ultraviolet rays. All of these different kind of rays that you maybe have heard of before, but didn't realize that that is light. It is. It's just not visible light, so you can't see that kind of light with your eyes. You can't see microwaves or X-rays or ultraviolet rays with your eyes because our eyes are only able to see visible light. But there's all kinds of different types of light that exist, and the sun gives off energy in all of those different forms. Okay, the visible light that it gives off is just a very small portion of the amount of light and radiation that it gives off. So the main question here then is, of course, well, what is the source of this energy? Where does this light come from? Does it burn some type of fuel like oxygen, or maybe there's something inside the sun burning? And if so, how long is it going to be burning before all that fuel is used up? So the process here that the sun uses to create energy isn't a chemical process. So when you burn something, like you light something on fire, that's a chemical process. You're taking oxygen in the air, and the thing that you're burning is providing a fuel, and the oxygen and that thing are combining together to create energy, which then is the heat and the fire that you see, and that's a chemical reaction. The sun works on a nuclear reaction. So nuclear basically means that you're taking atoms and you're fusing them together, or you're ripping them apart. But in the sun, it fuses them. So the sun goes through a process called nuclear fusion, where it takes two hydrogen atoms and it smashes them together hard enough that they fuse into one new atom, and that new atom is helium. Okay. Now this is very difficult to do. The sun has obviously an immense amount of gravity inside of its core, so there's a lot of pressure to smash these things together. But this is something that we humans can't really do very well. We can do nuclear fusion on a very tiny scale, but it requires an enormous amount of energy to fuse atoms together, and it's not viable for us to do this on a large scale to like power cities and stuff. If we could do nuclear fusion on a large enough scale, we could power the entire planet very easily with the amount of energy that nuclear fusion provides, but it's not very easy for us to do. However, the sun, of course, has no problem doing this because the sun is humongous and it has tons of gravity to smash these things together. And in this process, it releases a lot of energy, which is essentially what heats up all the gas and stuff on the sun. And then when that gas heats up, it gives off light and it glows. It looks like it's on fire, and I guess it sort of is. The sun is made out of a plasma. Plasma is where you take a gas and you heat it up really hot so that it gives off energy and it glows, and it's basically fire. So the sun is primarily made out of hydrogen and helium. Okay, it's primarily made out of hydrogen and helium. the hydrogen fuses into helium, and then energy gets released, and it heats up all the gas, the hydrogen and helium gas, which then give off light and makes it look like the sun is on fire. And it is essentially on fire because it is a plasma, but it's not burning like you would burn things here on Earth. Okay. All right. As for the questions here, we're going to skip past these. I have a whole video of me going over the questions, so if you're curious what the answers are for these, you can go watch that video. But I'm strictly just going to be talking about the information. So, all right, moving on. Why does the sun remain stable over time? So, one, we know that the sun has been relatively the same for about 5 billion years. We know that because we can look back at the fossil record on Earth. We can see fossils of plants and animals and things like that. And basically, we make the assumption that if there were living organisms like plants and other animals, you know, millions and millions of years ago, then those things probably needed sunlight and energy just like current things today need sunlight and energy. So if there were things alive and stuff back then it's very likely the sun was pretty much the same then as it is now, and nothing has really changed. So it's been fairly stable for, we think, about 5 billion years. Now, in order for the sun to be stable, there's two forces that are always acting on it, okay? The sun, if you think about it, is like a giant nuclear bomb that's just exploding all the time. When you take two atoms and you fuse them together, they create an enormous amount of energy. And the sun does this every waking second, tons and tons and tons and tons of times over and over. So the sun's essentially like a bajillion nuclear bombs just like exploding nonstop all the time. Which, if you think about it, then it should just go poof, or just blow off into a million pieces. But it clearly doesn't, right? And that's because gravity is working on the sun to try to crush it down to this tiny little ball. Gravity's job is always trying to take big objects and crush them down. And so the only reason why the sun doesn't blow up into a million pieces or get crushed down into a tiny ball is these two forces are balanced out. So the sun is constantly trying to explode itself, while gravity is always trying to crush it, and those two things are in equilibrium. They're balanced out with each other, they're equal, so the sun primarily just stays the same size the whole time. Now granted, that won't last forever. Okay, eventually the sun will run out of fuel, and gravity will win and it will crush it down, but for now, it's stable. Okay, so the energy from nuclear fusion in the sun pushes outward. We call this thermal pressure. The word thermal means heat. So it's essentially like heat pressure, right? The pressure of making energy and heat, while at the same time gravity is always kind of pull the sun inward and crush it down, and then these two things balance each other out, okay? So the sun remains stable because the outward pull, the inward pull of gravity and the outward push of thermal pressure from nuclear fusion are equal to each other, and the sun stays the same size. All right. Moving on. So let's talk about the structure of the sun. Okay, so the sun is actually made up of a bunch of different layers, sort of like an onion or like an ogre. And basically, we think of the sun in two distinct parts. Okay, there's the inner part and the outer part. So we're first going to talk about the inner layers, and then we'll talk about the outer layers. So the sun has three inner layers. It's the core, the radiation zone, and the convection zone. Okay, we'll go through each of these layers individually, and then we'll talk about the outside layers. So the core, as it sounds, is the very center of the sun. This is where nuclear fusion is happening. This is where the hydrogen atoms are getting smashed together to make helium, and energy is produced. The core is pretty small, obviously. It only has a diameter of about 400,000 kilometers, so a little more than a quarter of the diameter of the entire sun. But this is where all the energy is produced, and there's a very, very, very high amount of pressure and heat and gravity in the center of the sun. Okay, moving then from there, so energy gets produced in the core, and it moves out to the next layer. The next layer is called the radiation zone. So this layer you can't see by looking at the sun because it's underneath the surface. But in this layer, energy from the core travels outwards, and it travels outward in two ways. In this layer, it travels out by radiation. So radiation is where energy gets released and then absorbed by a particle, and then that particle releases the energy again, and then another particle absorbs it, and then it releases it and absorbs it and releases and absorbs it, okay? So radiation is when something gives off something else, and then it absorbs it, and then it gives it off. So the energy from the core think of it like a little pinball, and it kind of is like bouncing around as it gets shot out and reabsorbed, and then shot out this way and reabsorbed, and shot out this way. And so it actually takes a very long time for the energy from the core to get through the radiation zone. Scientists call this energy, as it moves through this, they call it the random walk, because the energy will just kind of get shot out in random directions, but eventually, just by probability and chance, it will eventually make its way out of the radiation zone. But it could take thousands of years for the energy to get out of this layer. Okay, so this radiation zone is where energy is absorbed and re-radiated or re-emitted. Okay, once it does get outside of the radiation zone, then it gets into the convection zone, and this is where things kind of get a lot faster. So the convection zone. Convection is where heat rises and cold things sink, right? Most of you guys know that hot air like rises up and cold air sinks down. This is known as convection, right? So hot things rise, cold things sink. Hot things rise, cold things sink. That's called convection. So when the energy gets to the convection zone, it rises to the surface of the convection zone very quickly, typically following convection currents, or these big like columns of heat, and then cold stuff on the surface of the convection zone sinks back down towards the core. It gets heated back up, and then it rises again. And so the convection zone for the sun is constantly churning itself like this, as hot things down here rise up and cold things sink back down. And this happens very quickly, so way faster than in the radiation zone. Okay, so this is what occurs in the convection zone. So far, this little image kind of shows we have the core in the middle. We don't need to worry about like inner core, outer core, but we have a core in the middle. Then we have the radiation zone, which is right outside that, and then the convection zone, which is right beyond that. And that's the majority of the sun. The layers on the outside of the sun are much thinner compared to those three ones. Okay, so the majority of the sun's mass comes from those three layers. All right. As for the outer layers, we call this the sun's atmosphere. So the sun's atmosphere, or outer layers, consists of three layers: the photosphere, the chromosphere, and the corona. Okay. So the photosphere is the innermost layer of the outer layers. I know it's confusing, right? So there's outer layers that are out here, and the photosphere is the innermost one. So it's the one like closest to the center of the sun. It's called the photosphere because this is the layer that if you were to look at the sun, and don't look at the sun, please, but like take a picture of it, or just sort of look at it from like your peripheral vision. This is what you're looking at. Okay, this is the layer that you see in photos of the sun or images of the sun, is the photosphere. It's very thin. It's only about 500 kilometers thick, so that's not very thick at all. It has an average temperature of about 5,800 Kelvin. So just to give you a relative idea of how hot that is, blowtorches are, about as hot as that, or a bit hotter. So it's not super hot. I mean, it's hot, but it's not that hot. The core is way hotter than this. Okay, so it's relatively cool or cold. And this layer, of course, isn't solid because none of the sun is solid. It's all gas. But we would consider it the sun's surface, right? So you couldn't walk on it, obviously, but when you look at the sun, this is the surface that you're essentially looking at. The easiest way to remember this is if you were to take a photo of the sun, this is the layer that you're looking at, okay, the photosphere. So beyond this, then we get to the chromosphere. Now, the chromosphere is even thinner than this layer. And here's the weird part. Temperatures from so going from the photosphere to the chromosphere, right? So you're getting further away, you're getting closer to the edge of the sun. You would think that the temperatures would go down. And it's actually the opposite. The temperature here is hotter than on the photosphere, which again is weird because you're getting further away from the center of the sun where all the heat and energy is produced. You'd think it would be getting colder, but it's not. It's getting hotter. There's a reason for that, and we'll talk about that in the last layer called the corona. But this layer is about double the temperature of the photosphere, and this layer is only visible during a solar eclipse. Okay, you can't see this layer most of the time because the photosphere outshines it, and this layer is very thin. So unless there is something blocking most of the sunlight or most of the light from the photosphere, you can't see this one. Oh, excuse me. Whereas during a solar eclipse, the moon goes in front of the sun, so all you can see is the outside edges of the sun, and then this layer is visible during that time. Okay. Lastly, the final layer we have is called the corona. Now the corona is even thinner, and it's the very further outermost edge of the sun, and it doesn't really have an end. It just kind of like wisps off into space. This is the second hottest layer of the sun. Now again, this is weird because you would think that this would be the coldest layer, right? We're the furthest away from the core. Things should be cold out at this part, but it's actually not. It's the second hottest. Temperature is about 1,000,000 Kelvin. Now, as to why is this the second hottest layer? It doesn't make any sense. There's a reason, and here's why. The sun is made out of a lot of charged particles. Okay, there's a lot of gas, and that gas is very highly energized because it's getting heated and stuff all the time. And so those particles of gas have electric charges on them, and they create magnetic fields. And the sun doesn't spin. So by the way, the sun rotates. Okay, it's like a big ball of like putty, and it constantly is turning and moving. But like the Earth all rotates at the same rate. The sun doesn't. Okay, the middle of the sun moves at a different rate than the top and bottom of the sun. So imagine that you've got like this sphere that's made out of like putty, but the top and bottom are spinning at a different rate than the middle is. So things start to get really twisted really quickly. And there's a lot of magnetic field lines that are on the sun that get twisted too when these things rotate. And so imagine that it's like you have a slinky, and this slinky gets all twisted up, and eventually, if it twists enough, it'll break. And when that happens, when those magnetic fields break, they release a lot of energy, and it causes all the gases around them to get heated up even more. Okay, so the corona is actually the second hottest layer because there's all these magnetic field lines that are getting twisted on the outside of the sun, and when they break, they cause the temperature to just skyrocket. Okay, otherwise, if that wasn't the case and the sun all moved at the same rate like Earth did, then this would be the coldest layer, okay, but it's not. So this also can only be seen during a solar eclipse. It's very, very thin. You can't see it otherwise. And again, it extends for millions of kilometers above the chromosphere, and it doesn't really have an end. It just kind of gradually thins out and floats off into space, and it turns into what we call the solar wind, which is a stream of very highly electrically charged particles that flow outward from the sun and just kind of spew off in all directions, okay? The solar wind certainly does go towards Earth. It does come and hit us here. Sorry, long night. And when these charged particles hit Earth's magnetic field, the magnetic field luckily deflects a lot of them back into space. But sometimes they can work their way through our magnetic field and they hit the surface of our atmosphere. And when that happens, these particles energize the gases in our atmosphere, and when those gases get energized, they give off light. And this is why the northern lights happen. This is why the southern lights happen, or the auroras, as we call them. And the reason why they happen at Earth's magnetic poles is because if you've ever seen an image of Earth's magnetic field, you have field lines that come out from the pole and they come around like this and they go back down to the bottom. So there's two little holes on the top and bottom of our planet where the magnetic field comes out from the planet. And so the particles can work their way down through those poles and get through the atmosphere there. Whereas around the equator, there's no openings there. So that's why the auroras, the northern and southern lights, don't occur in the middle of the planet. They only occur on the top and the bottom of the planet. Okay, so if you want to see all the layers again, here we have the core, the radiation zone, then the convection zone, and then here we have the photosphere is very, very thin. The chromosphere is this kind of glowy little layer beyond that, and then the corona is just this kind of really wispy stuff way on the outside. It kind of just looks like fog. Okay, so very, very thin. All right. As for some features that the sun has on its surface, there's three main ones we're going to talk about here. Okay, sunspots, prominences, and solar flares. Sunspots, if you've ever seen an image of the sun, you might notice it has these like dark spots on it, or almost like blemishes. It's kind of strange. So these are known as sunspots. And basically, they are regions where the material on the surface of the sun is cooler than the stuff that is around it. Okay, so because the temperature of this sunspot is much cooler than the things around it, it gives off less light, and it looks like it's dark. Okay, it looks black. However, if you could take that black sunspot off of the surface of the sun and look at just that, it would be very, very, very bright. It just doesn't look bright in relation to other stuff around it. So they look dark, but in reality, they're really not. Okay, they're very, very bright. They're way brighter than you might think they are, and they're very big. They look small, but the sun is enormous. So even these little black spots on the sun, which look small, if you could pull them off, they'd be larger than planet Earth. I mean, they're huge. Okay, so sunspots happen all the time. And a lot of times they give us an idea also of how active the sun is. The more active it is, the more sunspots it will have, and that can also be dangerous, and we'll talk about that here in a second. Another feature we have from the sun are called prominences. So these are where gases follow the magnetic field lines of the sun, and they kind of arc their way up through, up above the sun's surface and come back down in these giant flame loops, basically. Okay, this is how we know that the sun has a magnetic field and the lines are all twisted, because these flame loops are following the magnetic field lines of the sun, and we can see that they're kind of twisted all over the place. Okay, now again, these loops might not look that big, but they're huge. You could take the planet Jupiter, which is the biggest planet in our solar system, and fit it through one of these loops like no problem. Okay, like piece of cake. These loops can be like really, really big off the surface of the sun. And the other part is they can break, right? So again, imagine that these loops are like slinkies and they get all twisted and they can break. And when they do, they just fling this electrically highly charged particles of material off into space, sometimes off towards the middle of nowhere, and other times it can be flung right directly at us here on planet Earth. And when that happens, it can have really, really big impacts on our electrical power devices and power lines and satellites and all kinds of stuff. So when that happens, we call this a solar flare. Okay, so solar flares are where the sun's surface will just erupt, whether it be a prominence breaking or a sunspot releasing energy, and all of these charged particles just get blown off into space, and they can get released at planet Earth. And when that happens, they have, again, a lot of energy and a lot of electrically charged particles that can interact with electrical things here on Earth. And this can be really dangerous because if we're not prepared for it, it can knock out power grids, it can knock out satellites, it can cause blackouts in cities for very long periods of time. And you might not think like that's a big deal, like, oh, we lost some power, you know, that happens here every once in a while. Yeah, okay, well, maybe your house loses power for like an hour, 2-3 hours, whatever. Imagine a blackout for a week or weeks because power lines and stuff are blown. It's very, very dangerous, mainly because when that happens, there's no running water, there's no refrigeration. People start panicking because of food. In fact, even now with this whole COVID going on, we see the effects of people hoarding things or looting and stuff occurring. So it can be very dangerous if that happens, not to mention our whole communication system and banking information, all of that is essentially run off of satellites. So if satellites are in space and they get hit by a solar flare and they're not ready for it, they can just get completely knocked out permanently. And now we've lost communication around the planet. We've lost ways to transfer electronic information. So it can be very dangerous. But fortunately, there's a whole part of our government that essentially monitors the sun. And when there is a solar flare that could potentially come towards Earth, they warn companies and other places so that they close their satellites down or they power things down so that if the solar flare were to hit Earth, they're not going to get damaged because the circuits are already off. And damage really only occurs when electricity is running through them, and then the solar flare hits, because then they get overloaded and then they can essentially break. So... all right, anyway, so again, there's some more questions here, but they have a video of me going over those. So that's it for the information here. There's some videos on it that you can watch to get more info on it. But otherwise, if you have any other questions, you can always email me. All right, guys, that's it for this one. I will see you in chapter 26.2. Bye.